All right, guys, remember this one. Look at the rectangles that are formed, right? Remember we did this in class, so we're going to review this, look at the PowerPoint that goes along with this and a couple other problems so that you're set straight on those problems I gave you for homework, okay? That we're going to need to know for your upcoming test. Get it together, all right? Here, what were we doing? Trying to find the rectangle of maximum area, right? The perimeter was fixed, never changed. It was at 64. Infinitely many rectangles that can be formed, okay? Only one of which has the largest possible area, and that happens to be when this is a square, okay? So when the sides are 16 by 16, the area is maximized. Now, we're going to go through that development with you on a PowerPoint, so I'll be right back with. So we're back here and we're looking at this PowerPoint. So let's execute this PowerPoint because we have that problem to look at and a few others, okay? So we're talking about optimization. We're talking about quadratic optimization, all right? And optimization, of course, means either finding your maximum or your minimum, okay? So take a look, all right? Here was our situation, okay, um, where we had all the possible rectangles that could be formed. So with a perimeter fixed at 64, we looked at all these possible arrangements, 2 by 30, a 6 by 26, 10 by 22, onward and onward, okay, and looked at all the possible arrangements. What we do know for certain, though, is that the perimeter never changed. The perimeter was 64, and of course, the perimeter is determined by the sum of two lengths and two widths, okay, and since the perimeter was constant at 64, that's kind of a constraint we have with our problem. So on that basis, we got a relationship, a length to width relationship here, saying that L plus W is 32, or the length is 32 minus width, okay? Or the width is 32 minus the length, really doesn't matter which way you look at it. But what we need is a function. We need a function if we need to optimize this, okay? We need a function. So we know a formula, we know a simple formula, length times width, okay? But that's not a function. So if I wanted to, I find a function, the area as a function of width, in which case I say, okay, well, since the um, since the length is 32 minus the width, I can come here and I can say, instead of L times W, I can say W times 32 minus W, which gives me a quadratic, as you see here, the graph of which looks like this, okay? So this is the graph, uh, whereas we have the horizontal y-axis representing the area, and the width along the vertical axis is the area, and the horizontal is the width. And of course, what we're after, since we're after the greatest area, that's going to be at the high point of the parabola, which is the vertex, which is, okay, determined by the negative b over 2a formula, okay? So the negative b over 2a from here would clearly tell us that, okay, uh, the value of w would be 16, and of course, since 16 was w, we go back and say 32 minus w is the length. That's also 16, which illustrated um, that the rectangle of greatest area would in fact be a square. Okay, so let's build on that a little bit. I do want to put a limitation on w, even though this function as a function unto itself, the domain is all w's, but for practical applications for what we were looking at, w representing the width would not be 32 because, or it'd have to be between 0 and 32. Otherwise, you wouldn't have a box, okay? Here's another follow-up problem of the same variety, okay? So the rectangular region is to be fenced in. But we only need three sides of the fence because the building, which is going to serve as a fourth side, is going to be a barrier. So what we need to do is we want to find the dimensions of this rectangle uh, uh, with the greatest area. where only two sides of the rectangle are needed to fence in. So I'm designating again, here's, and you'll find problems in the book, of the ones I gave you, that are of this variety. So here you go. The two sides of the rectangle are X and one side is Y. We got 100 feet of fencing, so that's to imply that the sum of the X, Y, and another X is going to equal 100 feet. So we've got 2X plus Y is equal to 100, which again, we're going to want to optimize this area, and the area is going to be, of course, X times Y. So we were able to find Y in terms of X through the perimeter relationship, okay? And we're asked to find the rectangle of greatest area. So here again, X times Y is the area. X is fine. Y is 100 minus X. Putting them in place, of course, gives us another quadratic function. The area is a function of X. As you should see, that's quadratic. It's a downward opening quadratic. Okay, so the quadratic equation that maps the area as a function of X here is negative 2X squared plus 100X. Negative B over 2A would find us our high point, okay, which would be 25. Okay, since 25 is the value of X, we can come back to this equation, which says that Y is 100 minus X. So Y is 100 minus X, or Y is 100 minus 2X. That's what it should say up here, excuse me. So Y is equal to 50, okay? Another similar problem. Four adjacent regions, as shown, are to be divided using 2,000 feet of fencing. So here's the area, okay? But that area is split by fencing into four regions. Whether those regions are equal or not does not matter, okay? Because what we're trying to figure out is with this 2,000 feet of fencing, let's try to get the maximum area enclosed. Let's try to get the maximum area enclosed, okay? So again, it's going to be that relationship between the area and the perimeter, okay? The area is, of course, X times Y. We need an area function, so we need to get this one variable Y in terms of X, but then here we enter with the information provided from the problem. The 2,000 feet of fencing is equivalent to the perimeter, okay? So we have a perimeter of 2,000, but that perimeter is broken up into two lengths of Y and 1, 2, 3, 4, 5 lengths of X, okay? So we realize that, okay? So here it is. The perimeter, which is 2,000, is determined by 2 lengths of Y and 5 lengths of X, okay? And that perimeter is 2,000. So we can obviously solve Y in terms of X from there, okay? In which case we get Y is equal to 1,000 minus 5 halves X, okay? That should be simple enough to see how we get that, okay? And then, of course, the overall area, the area, the largest possible area that can be contained with that 2,000 feet is simply going to be the overall area of X times Y. So the overall area is X times Y, okay? Y is being replaced with this 1,000 minus 5 halves X, so that's the length of X times Y, which is minus 5 halves. That should be X there. Doing our distributing, okay? With our distributing, we can see that that function goes quadratic. That quadratic function is, again, a downward opening parabola. The vertex is going to be the highest point. That's going to represent the value of X, which produces the largest possible area. Negative B over 2A is computed as, okay, that should be, it somehow didn't show up here. This is negative 5 halves X squared plus 1,000 X, okay? So that's 1,000 X. You can see that. That's just a typo there, so be mindful of that. So negative B over 2A is negative 1,000 over 2 times 5 halves. So that means our lengths of X are going to be 200. And of course, we have 5 lengths of X at 200. So you got 200, 400, 600, 800, 1,000. You got another 1,000 feet from from the 2000, which is going to be split at 500 and 500 for the Y lens, okay? So the dimensions of the rectangle with the largest area, as you can see here, are going to be a length of 200 in X and 500 in Y, okay? So we'll come back and do another video and with some additional problems.